for your attention. So so today I'm going to be talking about some recent work that I've been doing with Professor Junqiao Xu on the approximation theory of shallow neural networks. So my plan is basically to give some background, talk about what shallow neural networks are, what problem we're trying to solve, and then I'll discuss basically the space of functions that can be efficiently approximated using shallow networks, and then the results that we've obtained, studying the properties of this space, and the approximation rates that can be obtained here, and then and then to conclude, I'll discuss some algorithmic aspects. How can you sort of algorithmically obtain the approximation rates that we're going to derive using greedy algorithms. Okay, so let's start with the background. What is a shallow neural network? Right, a shallow neural network is basically just a function which is given by a linear combination of plane waves, essentially, or ridge functions, as they're also called. Sigma of omega dot x plus b, basically a function that only varies in one direction with profile sigma, right? And so shallow neural network is just a superposition of these functions. And then this profile function sigma is called the activation function. And some typical examples that we'll consider are, say sigma is the heavy side, or a smooth version of the heavy side. This sigmoidal, right, is essentially a smooth version of this heavy side. These were activation functions that were initially studied a lot and important in machine learning and neural networks. And recently, the activation functions that have become more popular are these rectified linear units and the kth power of the ReLU. So right, this ReLU function or hinge function is basically like the integral of the heavy side, and ReLU to the k is a kth power here. So there's a bunch of other activation functions people have considered, but in this talk we'll basically just stick with these four, essentially: heavy side, sigmoidal, the ReLU, and ReLU to the k. So we're interested in the approximation properties of this class of functions. So we want to know which functions can be approximated by these shallow neural networks and how efficiently. So an initial question and basic question to ask as well is this approximation method sort of universal, right? In the sense that given any continuous function, can I approximate it to arbitrary accuracy with a sufficiently wide shallow neural network? Or in other words, is this class of shallow neural network functions dense in the space of continuous functions? Right? If this is not true, then it's probably not a very good class to consider, right? Of course, this is going to depend on the activation function, right? If your activation function is too simple, if it's, say, a linear function, right, then these shallow neural networks are all going to be linear functions. Or if it's a polynomial, your shallow neural networks are all going to be polynomials of the same degree. So for these very simple activation functions, this class is not dense, but it turns out that that's the only restriction there is. So if your activation function is just not a polynomial as anything else, then at least in principle you can approximate any continuous function using a shallow neural network with this activation function. And this result goes back quite a bit. So this is a pretty old result. But of course, our question is, well, how wide does the network have to be? Or in other words, how many terms do I need in this expansion in order to accurately approximate a function? So how efficient are shallow neural networks at approximating certain functions? And in particular, we're going to identify a class of functions which shallow neural networks can approximate efficiently, and then our goal is to try to show that these shallow neural networks are optimal in a certain sense on this class of functions we're going to find. So that's kind of the roadmap, is let's try to find a class of functions that shallow neural networks can approximate efficiently, and then determine how well they do on that class of functions, and then show that they're optimal in some sense. So those are the questions we're going to ask. All right, so the next thing I'm going to do is introduce this class of functions. Basically, answer the question, what is the class of functions that shallow neural networks can approximate efficiently? And the sort of proper way to introduce this is to look at a slightly more abstract situation, which is that of nonlinear dictionary approximation. So here I'm going to say, suppose I take some Banach space, like, a typical example would be like LP on some domain in RD. And now I'm going to just pick a collection of functions in there called a dictionary, right? So this is an approach that's taken in machine learning and statistics, right? Is you can think of this D as being some sort of frame, maybe in signal processing, or really in our case there's no real restrictions, just some arbitrary collection of functions in my Banach space. And my goal is to try to approximate functions, or to approximate elements F in this Banach space by n-term dictionary, n-term linear combinations of dictionary elements, right? So here, given an F in X, I want to approximate it by an expression of this form, where crucially, right, the DIs, the dictionary elements that occur in the expansion, depend upon F. And so that's why it's called a nonlinear dictionary approximation, because the DI that show up in this expansion depend upon the function F. In some sense, it's kind of like a sparse representation in terms of this dictionary. So the space of functions that, so again, the question is, which class of functions can be efficiently approximated using these nonlinear dictionary expansions? And the class of functions we're going to consider is basically the convex hull of the dictionary, right? So here, it's basically the convex hull of plus or minus the dictionary, right? So we're taking all linear combinations of dictionary elements, arbitrarily many dictionary elements, but we require that our coefficients here are bounded in L1, right? So we take that's exactly the convex hull of plus or minus D, and now we take the closure of this set with respect to the norm on X. Okay, so this is the class of functions that we're going to consider approximating by nonlinear dictionary expansions. And so for convenience, we can associate a norm to this class of functions, right? Because since this is the convex hull of your dictionary, right, it's in particular a convex and symmetric set, so we can define a norm, right, whose unit ball is exactly this set, which is called the gauge norm, right? We just set the K1D norm of a function F to be the smallest multiple of that ball that contains F, right? And this norm exactly has the property that its unit ball is this convex hull, is this class of functions we're interested in. So it turns out, if the dictionary D is uniformly bounded, right, with respect to the norm on X, then this space here with the norm, with this K1D norm, has some nice properties, right? It's a Banach space, but that's what we're the class of functions we're going to consider going forward is exactly this convex hull of your dictionary, and it has this associated norm. Okay, so a very simple example of this is, suppose that we take the sequence space little LP, and we let our dictionary just be the standard basis of this space. In this case, the convex hull of this standard basis is, of course, going to exactly give you the unit ball of little L1, right, contained in little LP. And then, so suppose we want to do nonlinear dictionary approximation in this situation, right? We have a vector in L1, or an element of little L1, and we want to approximate it in little LP using a small number of components. So of course, the best way to do that is to take the largest coordinates, right? The largest components. And in this case, you can easily verify that you get an approximation rate here of n to the 1 over p minus 1. So if p is bigger than 1, you do get an approximation rate then for this class of functions. And but this is, of course, a very simplified situation. What we really want to do is consider the case where the dictionary D is basically an arbitrary subset of our Banach space, not this particularly simple situation, right? In that case, things can be a bit more complicated, and in particular, neural networks are an example of this, where for certain dictionaries D, right? That's the next thing we'll discuss, right? So this is a very simplified example. We'll look at a more complicated situation next, right? So in particular, how is this related to neural networks? Well, if you give me this activation function sigma and some domain that you're interested in approximating your functions on, if we consider the dictionary consisting of all of these plane waves, right? The dictionary consisting of all sigma of omega dot x plus b, all of these ridge functions. Now, for certain sigma, and we'll discuss this in a second, we need to restrict omega and b in order to ensure that this dictionary is bounded. But for the moment, let's not worry about that. So given this activation function sigma, we consider this dictionary of all of these plane waves with profile sigma. And then in this case, right, nonlinear approximation from this dictionary corresponds exactly to approximating by shallow neural networks with width n, of course, right? Because we're taking a linear combination of sigma of omega dot x plus b's, and these omega I and bi, as in addition to the coefficients ai, depend upon the function that we're trying to approximate. Okay. So let's look at some concrete examples of activation functions and see what this space looks like. So first, let's consider the Heaviside activation function, right? The one that just jumps from 0 to 1. So here, sigma of omega dot x plus b consists of the indicator function of a half space. So now what we're essentially doing is we're taking all of those indicator functions of half spaces, right, and taking the convex hull of that in LP, the closed convex hull of that. So if d equals 1, right, this just corresponds exactly to shifts of the Heaviside function. Right? If I take shifts of the Heaviside function, look at all possible shifts on some interval, and take the convex hull of that, it turns out you get exactly the space BV of bounded variation functions. And moreover, if I replace this Heaviside activation function by a smooth sigmoidal function, so if I smooth out this Heaviside, then it turns out we'll get the same space, right? That's generally true, is that kind of the sigmoidal activation function behaves essentially like the Heaviside in terms of approximation properties, right? It's certainly doing gradient descent or something is a lot easier with a smooth sigmoidal activation function, but in terms of being able to approximate a given target function, behaves essentially like the Heaviside. Okay. So another important example we'll look at, right, is the ReLU activation function. And this is a case where I can't just let my dictionary of functions be sigma of omega dot x plus b for arbitrary omega and b, because that dictionary would not be uniformly bounded in LP, right? If I make omega or b large, I can make this function very large. So in order to get around that, we're just going to restrict these inner weights. So we're going to restrict omega and b to be in the sphere, right? So omega, the direction, has to be in the sphere, and my bias b has to be on some interval. This precise interval depends on omega, but if I choose omega to be the unit ball in RD, for example, this interval minus 2 to 2 will suffice, right? And there's more technical details in some of these references here. In this case, again, when d equals 1, we get a characterization in terms of BV. Basically, it's the set of functions whose derivative is in BV. And it turns out that also if, in this case, if d is greater than or equal to 1, we can get a characterization in terms of the radon transform of f. So if you look at basically the L1 norm of the radon transform of some derivatives of f, this exactly corresponds to the K1D norm on this class of functions on this convex hull. Okay. And similarly, we want to also do the same thing for powers of the ReLU. So if I look at ReLU to the power k, right here, this is basically a smoother function because the discontinuity at 0, you've got more derivatives matching. This is ReLU to the k. So again, you have the same issue with the boundedness of the dictionary, and we restrict the omega and b weights in exactly the same way. And again, you have a similar situation. D equals 1. You can characterize this by saying that a certain number of derivatives have to lie in BV, and when d is greater than or equal to 1, right, we can, for higher dimensions, we can also characterize this in terms of the radon transform. So this is the class of functions that we're going to be interested in when we talk about approximation by shallow neural networks with ReLU to the k activation function. Okay. There is another class of functions we'll also be interested in, and these are given by taking the convex hull of a different dictionary, what's called the Spectral Barron dictionary. So here what you do is you consider pure frequencies, right? This you would even probably really call plane waves. And except the larger the frequency is, the more we have to scale it down. So we take these Fourier modes, e to the 2 pi I omega dot x, and scale it down by a power of omega. And if you do this and you take the convex hull, right, then it turns out this class of functions is characterized by this condition on its Fourier transform. Right, so in fact, the norm of a function in this K1 FSD space, right? So if we essentially take the smallest multiple of the convex hull of this dictionary, which contains f, that's exactly equal to taking the Fourier transform of f and taking its L1 norm with this appropriate weight. Okay, so this weighted L1 norm of the Fourier transform, and this so this was introduced by Andrew Barron. And essentially the significance of this is it allows you to characterize a large class of functions that can be approximated well by shallow neural networks. So right, we can say is if the Fourier transform of a function with a certain weighting factor is in L1, then we know that it's in this convex hull and can be approximated efficiently in terms of efficiently using shallow neural networks. So that's why this space is kind of significant. It gives us a fairly large, or it gives us a subspace or a subspace of this K1 PKD, which can be characterized in terms of the Fourier transform. Right here, the amount of smoothness here you need in this for this Fourier dictionary depends upon how much smoothness you have for these ReLU to the k, right? So for ReLU to the k, you need s to be at least k plus 1, and then that's going to be contained in this space, right? So yeah, the significance there is you can characterize some of these functions in terms of the Fourier transform. Okay, so before I move on, I just want to give some kind of history of where these ideas kind of come from. And so, convex hulls of elements in a Banach space have been studied, for a long time in functional analysis. In particular, some of these, these references are from the 1980s. People have been studying this sort of abstractly in functional analysis, and they started this notion of the convex hull of a dictionary started to play a more important role in machine learning and statistics and signal processing in like the 1990s. In particular in the theory of greedy algorithms for nonlinear approximation, and also for shallow neural networks, for the theory of shallow neural networks. This subject sort of goes back to the application to machine learning goes back to the 1990s. And recently, though, because there's been a big explosion in the field of neural networks, there's been again a sort of revived study of these spaces of functions given by the convex hulls of sigma of omega dot x plus b. So here's some references here's some references about sort of where these things come from. So these things have been studied for quite a while in statistics and machine learning. Okay. But the fundamental questions that we want to ask, and these haven't been yet completely answered, right? So there's still some open problems in this field, is what approximation rates can you obtain on this convex hull using shallow neural networks, right? So for this particular class of function, how well do shallow neural networks do? Another question is, can we show that shallow neural networks are optimal for this class in a certain sense? Right, this class of functions is very sort of specific to these shallow neural networks, right? It's given by exactly this convex hull, so it seems like like this would be a class of functions for which neural networks would be very good, but can we show that they're actually optimal for this class of functions? And then finally, can all of this be done algorithmically in some way? So those are the three questions that we want to try to answer here. Okay. So yeah, now let me go into the main part of the talk here. We'll talk about those first two questions, which are what approximation rates can be obtained, and are they, are shallow neural networks optimal for this space of functions? Here I'll consider everything in the Hilbert space L2, but we have some recent results on LP which we can discuss later. But yeah, so I'll stick to L2 here for this talk, and we'll discuss those first two questions now. So first, what approximation rates can we obtain on this convex hull? The key kind of argument here, the sampling argument, goes as follows, right? And this is for general nonlinear dictionary approximation in Hilbert spaces. So here, let's suppose that my space X is a Hilbert space, right? I've got some dictionary functions in X, and I'm going to consider some function in the convex hull of this dictionary, right? So being in the convex hull of this dictionary just means that I can write F as an expectation of some probability distribution over the dictionary elements, right? So essentially, being in the convex hull just means I can construct a random variable whose expectation is F and whose values lie in the dictionary. So the key idea is, if I want to approximate my function F by a nonlinear dictionary expansion, what I can do is I can sample from that random variable, right? So I just say, okay, the target function F is an expectation over this dictionary. I'm going to just construct an approximant by sampling n independent copies from this random variable F and taking the average, right? And now determining how accurate this approximant is becomes just a calculation of what is the variance of this average. If I form this estimator, what's the variance? And doing this calculation, we see, of course, the expected value of this empirical average is still exactly the target function, and the variance of that estimator goes as 1 over n. Okay. That's just a fairly straightforward calculation, and this also works more generally, not just in Hilbert spaces, but in other types of Banach spaces as well. This should be greater than or equal to 2, and less than infinity. So what this tells us is that since the expected error then basically goes as 1 over root n, right, because the variance goes as 1 over n, there must exist some nonlinear dictionary expansion that achieves that rate, right? So this fundamental sampling argument is due to Moray, and it's from functional analysis from 1980s, and so, but this tells you, if you're approximating a function in the convex hull of this dictionary, there always has to, the rate of approximation is at least 1 over root n for these nonlinear dictionary expansions. So this has some notable consequences for neural networks, and this is what generated a lot of interest in the early 1990s, which is that, if I consider this convex hull, then shallow neural networks with a given activation function achieve an approximation rate of n to the minus 1/2, independent of the dimension, right? Independent of the dimension d here. So as long as you're in the convex hull of sigma of omega dot x plus b, you certainly get this approximation rate of n to the minus 1/2, right? And in particular, this also holds right for functions that satisfy a certain condition on their Fourier transform, right? If the Fourier transform is in L1, we know you're in some scaled convex hull here, and so this gives, for this class of functions defined by this Fourier transform condition, this gives an approximation, a dimension-independent approximation rate of n to the minus 1/2, and this was sort of the significance of this work by Andrew Barron. And this, of course, generalizes readily to neural networks with ReLU to the k activation function. In this case, you're just taking the convex hull of a different sigma of omega dot x plus b set. Okay. So this is sort of the starting point here, is that you can get these dimension-independent rates for shallow neural networks on this particular class of functions. But it turns out that these rates can actually often be improved a little bit further. So this O of n to the minus 1/2 rate that you get with this sampling argument can actually be improved in many cases. So the first result of this type was by Makovos, and he showed that if you look at neural networks with a Heaviside activation function, you look at this dictionary P0D, like the convex holes of sigma of omega dot x plus b for the sigma being the Heaviside, that in this case you can improve that rate from n to the minus 1/2 to n to the minus 1/2 minus 1 over 2d. Right, so you get, in high dimensions, this is maybe not much of an improvement, but you get this actual improvement on in the rate of minus 1 over 2d. And this was then also recently extended to sigma equals ReLU to the k, where it was shown that you can improve it. You can also improve this n to the minus 1/2 rate by a little bit to get n to the minus 1/2 minus 1 over d. So this n to the minus 1/2 rate you get by sampling can actually be improved a bit, and this is proved using a stratified sampling argument. You sort of sample in a clever way, and you use the fact that this dictionary is compact in a certain sense. So, yeah. So the point is this n to the minus 1/2 rate can be improved a bit, and in the specific case of the ReLU, there's also an even bigger improvement that can be obtained. This is due to Bach and using ideas from functional analysis that are due to Matusek. You can show that for sigma being the ReLU, the rate of approximation you can get is n to the minus 1/2 minus 3 over 2d. So that's better than the minus 1 over d before, right? And so this is where we sort of started to work on this problem, right? This is where our results start to come in. The problem we wanted to address was, what are the optimal approximation rates you can get, right? So you can improve beyond this n to the minus 1/2 sampling result, but how much, right? Can you improve these approximation rates even further? That was our question. Okay, so next I'll explain what we did, and basically it consists of two parts. We get upper bounds, so improved approximation rates, and lower bounds, showing that the approximation rates we get cannot be further improved, right? So we'll start with the upper bounds, and the key. So and what we proved here is that in fact for ReLU to the k neural networks, so if I make my activation function ReLU to the k, right, and I consider this convex hole, then the approximation rates that shallow ReLU to the k networks can attain are n to the minus 1/2 minus 2k plus 1 over 2d. So the improvement of the improvement beyond n to the minus 1/2 you get is minus 2k plus 1 over 2d. And so you can see if k is equal to 0, right, this would correspond to the Heaviside. You'll get exactly the result of Makovos, minus 1 over 2d, and if k is equal to 1, this corresponds to ReLU. You'll get exactly this Bach-Matusek result, minus 3 over 2d. But what we essentially did is we extended this to all k greater than or equal to 2. So this is the improvement that you get, right? And the way that we did this is we used what is essentially a higher order generalization of stratified sampling. So the key idea is to notice that the dictionary sigma of omega dot x plus b has a certain amount of smoothness in the following sense. So what we do is we'll say that a map, that we're going to consider a map from RD, so from some open set in RD into a Banach space. And we say that this map has a certain smoothness class S if for any element of the dual space, if I take the inner product with that element, the resulting function is in the S-order Lipschitz space. So in other words, it has k derivatives, and the kth derivative is alpha Hilbert continuous, right, where S is equal to k plus alpha, right? And you can of course generalize this to, if the domain is a smooth manifold, you define this in terms of charts, And what we do is we say our dictionary is smoothly parameterized to order S if there's a parameterization map, right, that contains the dictionary D. Okay, so let's look at some examples of smoothly parameterized dictionaries. So the ones we're going to be interested in, right, are these PKD dictionaries. So suppose I've got the Heaviside function here again, right? And what I mean by parameterizing the dictionary is, you've got a map from omega in the sphere and b in -2 to 2. You've got a map from this set into the space of functions L2 given by sending omega and b to sigma of omega dot x plus b. Right? So basically this plane wave of this ridge function is parameterized by omega and b, right? These and you then get this map from this manifold here, this d-dimensional manifold, into L2, and you can verify that this map is of smoothness class 1/2, right? What that means essentially is that the map is 1/2 Hilbert continuous. This is a calculation you can do basically if you look at the difference. That this difference is basically 0 outside of a set of width given by the difference between these two parameters, right? So there's omega minus omega prime, b minus b prime. That controls the width of, like, this difference here is 0 outside of a set with this given width, and on that set it's at most 1. So you can, it's a bit of a calculation here to verify that in fact this map is 1/2 Hilbert continuous. Okay, and similarly, you can look at these higher order powers of the ReLU. In this case, it turns out that if you look at ReLU to the k, it'll be of smoothness class k plus 1/2, basically because we can take k derivatives, and then it effectively becomes the same thing as having the Heaviside, sigma 0 here, and that is 1/2 Hilbert continuous. So in general, this is the result you'll get is that this PKD dictionary is of smoothness k plus 1/2. So then what we have is the following abstract theorem, which is that if your dictionary D is parameterized by a compact d-dimensional manifold with smoothness S, then you can obtain an approximation rate of n to the -1/2 minus S over D. So this improvement over the n to the -1/2 rate, you can get this improvement of S over D if the dictionary D is d-dimensional and is smooth to order S, right? And if you look at the dictionary PKD with which is smooth to order k plus 1/2, we get this rate n to the -1/2 minus 2k plus 1 over 2d, which matches. It extends this Bach-Matusek result to higher values of k, and improves upon this n to the -1/2 minus 1 over d, for larger values of k. Okay, so let me sort of briefly sketch a proof of this. Basically, what we do is we reduce to the case where the manifold M is a cube, and then what we do is, okay, this is kind of a technical reduction, but so suppose the manifold M is a cube. Now we subdivide the cube into subcubes, right? And if we are allowing ourselves n subcubes, the diameter is going to go as n to the -1 over d. And now what we do is we take the parameterization map, right? So the map that sends omega and b to sigma of omega dot x plus b, right? We take that map and interpolate it on each of these cubes, right? So we choose a set of interpolation points, CL, and then form a polynomial interpolation of this parameterization map on each of these cubes, right? So in total, it'll be a piecewise polynomial interpolation, which is a polynomial in each of the cubes. And then for a given function f, which is in this convex hole, right, which can be written as a sum ai p of zi, right, for some potentially very large number n, right, and n can be arbitrarily large. So we rewrite that then as f is equal to some average of the polynomial interpolant plus some average of the error. And now the key is that this polynomial interpolant, I'm only ever evaluating the parameterization map at CL, right? These guys are just coefficients. And so this first term has a fixed number of terms, right? There's a fixed number of dictionary elements, regardless of how large n is. So in that first term, there's always a fixed number of dictionary elements. And then to deal with the second term, we use the fact that right, we basically use a polynomial approximation lemma, a Bramble-Hilbert type lemma, to show that the error in this polynomial approximant is n to the minus s over d. And then we finally applied the original sampling argument to this error to get the result that we want. So in this sense, it's a higher order generalization of stratified sampling, because stratified sampling essentially approximates this parameterization map by a piecewise constant function. So if we use piecewise polynomials, we can obtain this improved rate. Okay. So that's how we get these upper bounds. That's how we have been able to improve the approximation rates for relative to the k networks on this particular space. So next, let's consider the problem of lower bounds, which is the question of, are those approximation rates optimal? How can we show that you cannot improve that n to the minus 1/2 minus 2k plus 1 over 2d further? And it turns out in order to do this, we need to make some assumptions. So at least we don't know how to do this with no assumptions on these AIs. But the assumption we're going to make here is, suppose that the coefficients of this nonlinear dictionary expansion are bounded. So these AIs are all bounded by some fixed value, right? So we'll introduce this new set, sigma n comma md, where now we're taking nonlinear dictionary combinations. Again, the DIs can depend upon the function to be approximated, but I'm going to force these coefficients AI to be bounded. And you can see that the upper bounds we previously had hold for this set as well. So now, it had previously been shown that with this additional restriction, you could not improve the approximation rate beyond n to the minus 1/2 minus k plus 1 over d, right? And if you compare that, for relative to the k networks, and if you compare that with the upper bound we got, there's still a gap of n to the minus 1 over 2d. Okay, so that was sort of the next question here was, can we close that gap and show that you cannot further improve our upper bounds? So
sorry. In this case, in your channel network, right? For instance, the Brazil case, do you also restrict the W in Sn or Sn minus 1 or St minus 1?
Oh yeah. So So for the relative to the k case, we always that's basically a restriction on the dictionary D. We always restrict the omegas and b's to be in that set.
So if you have the upper bound, which means you basically restricted the upper bound of the whole functional class.
Right. Well,
because the dictionary have a uniform upper bound, and AI you have a uniform upper bound. The whole thing you have a uniform upper bound. Is that right?
Right. Except this n can grow, right? So the number of terms could grow.
Sure.
Yeah.
Okay.
I mean, you could, I guess, a more standard thing to do would be to assume the AIs are bounded in L1. In that case, you actually cannot approximate anything that's not in that convex hole.
That's what I'm trying to ask.
Yeah. Oh, right. Yeah. So here we relaxed it a little bit, right? To say, let's just. I mean, it seemed to us to be a bit strong of a restriction to force the AIs to be bounded in L1.
Yeah.
Right, because then you can only approximate things that are in that convex hole.
Exactly.
But you can still get the same lower bounds if you relax this to being just AIs bounded in L infinity, which seems to be more natural restriction, I think, easier to justify. Yeah.
Okay, thanks.
Sure. Yeah. Any other questions at this point? Okay. Yeah, so with this restriction, you can obtain lower bounds on the approximation rates, but in particular there still is a gap between the best lower bound previously obtained and the upper bounds we had. So our question was, can you close this gap of n to the minus 1 over 2d? And that yeah, so it's basically that's what we did next, right? So it turns out that under this restriction on the L infinity norm of the AIs, you cannot improve this approximation rate. So for any delta and for any bound on the AIs, you cannot improve beyond n to the minus 1/2 minus 2k plus 1 over 2d. We don't know if maybe it's possible to do that with no restrictions on the AIs at all, but with that restriction, we can show the lower bound. We can show this lower bound and show that the upper bound cannot be improved. Okay, and the method we use to obtain this lower bound is based on the concept of metric entropy, which we also believe is quite important for understanding what's happening here. So the metric entropy of a class of functions is basically defined as follows. Given this class of functions in a Banach space X, I'm going to try to cover my class by 2 to the n balls of some radius, and I want to know how small can I make the radius while still being able to cover this class. And in a sense, it's a measure of compactness, because as n goes to infinity, because right, if you can do this, right, your set is certainly going to be compact, right? So in a sense, it's a measure of compactness. How many balls of radius epsilon do we need to cover the set B? If you can cover the set B by balls of arbitrarily small radius, that's exactly what, by finitely many balls of arbitrarily small radius, that's exactly what compactness says. But this is, the entropy is asking the question, how quickly does the number of balls grow as epsilon goes to 0, right? So here this relationship is written as an epsilon in terms of n. If I allow you a budget of 2 to the n balls, how small can you make? How small can you make them and still cover your set? And what this quantity measures is basically how accurately elements of the set can be specified with n bits. So if I try to discretize this using n bits, which allows me to distinguish a total of 2 to the n functions, what accuracy can I obtain? So a simple example here, right, is one-dimensional example is if you look at say the interval of 0, 1 in R, then if I discretize this, the best thing to do is to have evenly spaced points, and there you can get an error of 2 to the minus n with n bits. Of course, in general, the case we'll be interested in, right, is where x is some function space, some infinite dimensional Banach space, and b is some class of functions. In this case, often the metric entropy here will decay polynomially. And because of this characterization here, it gives a fundamental limit for how well any sort of numerical algorithm can approximate or learn functions from your class. Right? Because even with n bits, you cannot do better than the entropy. Okay, so the relationship between the entropy and this lower bound we have here comes from the following result. So suppose that I have some dictionary which is compact in a certain sense, in the sense that it can be covered by polynomially many balls of radius epsilon. Then and I have some class of functions. So then if I can obtain an approximation rate on this class of functions using nonlinear dictionary expansions with these bounded coefficients of n to the minus alpha, then the entropy of my set has to decay like n to the minus alpha up to logarithmic factors. Right? So this is saying for the class B, if I try to approximate it with these nonlinear dictionary expansions, if I attain this rate n to the minus alpha, then my entropy must also decay at that same rate up to logarithmic factors, right? And the particular dictionaries that we're considering, which are PKD, right, this convex hull of ReLU to the k of omega dot x plus b, and d sigma d, where sigma is a sigmoidal function with bounded variation. These two dictionaries, turns out, do satisfy this assumption, right? This polynomial covering assumption. So in particular, this theorem applies to these particular dictionaries. right? And so now the point is that by lower bounding the entropy, the metric entropy of this set, I can obtain a lower bound on the approximation rates that can be achieved. And so that's exactly how we proceeded, right? We then took this class of functions, this convex whole of our dictionary, and we lower bounded its entropy and showed that the entropy is lower bounded. Its rate, right, goes as n to the minus 1/2 minus 2k plus 1 over 2d. In fact, this is exactly the rate of decay of the entropy. We also got, remove the logarithmic factors to get a matching upper bound. But more importantly, this implies that the approximation rates we attain for these relative decay networks are sharp, right? At least the exponent cannot be improved further. So that's where that comes from, right? And of course, the estimation of the entropy of the set is also, useful in and of itself. But our main application was to show that in fact this n to the minus 1/2 minus 2k plus 1 over 2d rate that we had gotten cannot be further improved for at least on this convex whole. And let me just sort of sketch the proof of this, right? So this is proved by constructing a large class of almost orthogonal elements in this convex whole, in this class of functions. And so the idea is to use the following fact, which is that we know what the entropy of the L1 unit ball with respect to L2 is, right? So in dimension n, that scale, basically the rate is n to the minus 1/2. Okay, so this means if I can find a collection of functions in the convex whole of my dictionary, which are orthogonal, and such that all have length greater than c, right, then if I take, certainly this is a convex set. So the convex whole of F1 to F1 through Fn is also contained in B1 of D, right? Which means that I've essentially found a scaled image of the L1 unit ball in my class, right? Basically, I've found an L1 unit ball of size C in my class, and that tells me the metric entropy is lower bounded by, C over 2 n minus 1/2. So the previous results that I indicated, the previous lower bounds, are obtained by considering orthogonal frequencies and noting that, if these frequencies decay fast enough, this Fourier dictionary is contained. The convex whole of this Fourier dictionary is contained in the convex whole of these relative decay dictionaries, as long as the decay here is fast enough, right? By taking these orthogonal frequencies, you can actually get a rate of n to the minus 1/2 minus k plus 1 over d, right? So by choosing these FIs to be orthogonal frequencies in this convex whole, they have to decay at a certain rate depending upon which power of ReLU you're using. You can obtain the previous lower bound. To get that extra 1 over 2d, though, and to essentially show that this convex whole of these relative decays is strictly larger, in a certain sense, than the convex whole of this Fourier dictionary, you need to construct a larger collection of elements. In this case, you can't make them actually orthogonal, but you can make them nearly orthogonal, and that is, in an appropriate sense, and that turns out to be enough as well. So that these are the technical sort of details of how the proof works. We sort of, there's kind of a technical construction of a large collection of nearly orthogonal elements in this convex whole, and then we use the fact that we know the metric entropy of L1 of the L1 unit ball, essentially. Okay. So next, I want to talk about this question of optimality, right? So far, to summarize, right, we've introduced this class of functions given by the convex whole of these sigma of omega dot x plus b's, and we've looked at the approximation rates and determined, right, exactly what the approximation rates that ReLU to the k dictionaries can attain on that set, exactly what that is, right? Right, so we've got a particular class of functions, and we've worked out what the approximation rates for shallow networks on that class are. So the question is, can we show that ReLU to the k networks are optimal for this class? right? If we look at this, again, this convex hole, sigma k of omega dot x plus b, we've already determined how good shallow networks are on this class. Can we show that they're better than any other method, right, or optimal? So let's try to make this a little bit well defined, right? Because what exactly do I mean by optimal? So let's consider an abstract situation here where, again, you have some class of functions in a Banach space you're trying to approximate. An approximation method here, we'll say, is a pair of maps. One that maps B to Rn, you can think of this as taking a function in your class and mapping it to a set of parameters, of n parameters. And then another map, or sort of reconstruction map, where you take the parameters and you obtain a function in X, right? So the first map is kind of an encoding, the second map kind of a decoding or a reconstruction map. The encoding maps your function to a set of parameters, and then the decoding maps those set of parameters back to a function. And the error of the method is given by, for a given function f, it's the error, if I map it to its parameters and then map back, the error that I get here is that then I take the maximum over the set B, right, to obtain the error rate of this method. Right, this is very abstractly what I'm going to say an approximation method is. Of course, there are many questions like you want these maps to be, implementable somehow algorithmically and everything, but just abstractly suppose that, this is the notion we're going to take, and then this is the error rate of the method. So, in order to get non-trivial results, right? What we want to say is well, okay, shallow neural networks are going to be better than any approximation method on this set B, right? On this convex hole of sigma k of omega dot x plus b. Of course, that you need to make some restrictions on these encoding and decoding maps in order for this to make sense, because the cardinalities of these sets are the same. So, just mathematically, you have to put some restrictions there, and what restrictions you place determine what types of approximation methods you're studying, right? So we're going to consider two different restrictions on En and Dn, and show that with those restrictions, you cannot do better than shallow neural networks on this convex hole, right? So that's what we then mean by that. That's our notion of optimality. So the first restriction we're going to consider is, suppose that my decoding map here has to be linear, right? So my map from Rn to X has to be linear. This basically means that we're approximating the set B by a linear subspace of X. Okay, so we're using linear approximation methods. Then the second restriction I want to try to make is, suppose that the encoding map E has to be continuous. So if I have two functions in this class that are close, their corresponding parameters should also be close, right? So this is sort of a continuous but potentially nonlinear approximation, right? So the second case is you're considering nonlinear approximation, but you require the map from functions to parameter to be continuous. And the first case we're going to consider linear approximation, right? And then, so the appropriate notions in each of these two cases is, well, for linear subspaces is called the Kolmogorov n-width, right? So this right here, dn of b with respect to the norm x is just the best you can do with any linear subspace of dimension n, right? So the Kolmogorov n-widths measure exactly this first situation. How well can you approximate b by linear subspaces, right? This is just a definition. Of course, the difficulty is obtaining upper and lower bounds on this quantity, right? So for the linear approximation, the relevant notion are these Kolmogorov n-widths, and for this continuous approximation, right? So continuous nonlinear approximation, turns out that the right quantity are what are called the Bernstein n-widths. So here, what you do is essentially you look at subspaces of dimension n, and you take a ball of radius r. You take the largest ball in your subspace that's contained in the set B. This should be a B intersect Fn. It's a typo, sorry. So you take the largest ball in your subspace of dimension n that's contained in the set B, and then you take the subspace for which that ball is largest. That's what the Bernstein n-width is. It's a bit technical, but the key point is that the significance of these Bernstein n-widths is that they lower bound the best approximation you can obtain if you require that your map from function to parameters is continuous. So this is maybe a little bit more technical, but that's really the point, is this lower bounds the best approximation in this continuous approximation case. So now what we did is we lower bounded both these quantities, right? So we showed that the Kolmogorov n-widths decay like n to the minus 2k plus 1 over 2d, right, for this convex hull of these relative decay functions. And the Bernstein n-widths decay at least or bigger than n to the minus 1/2 minus 2k plus 1 over 2d. And this actually follows from this construction that we had of nearly orthogonal elements. But what are the consequences of this? Well, this first lower bound here shows that linear methods are much worse than shallow neural networks on this convex hull, because especially in high dimensions, right? Because you've lost this n to the minus 1/2, right? And in high dimensions, the n to the minus 1/2 is going to be most of the decay. So this is going to be this is going to decay much slower than n to the minus 1/2 minus 2k plus 1 over 2d. So from that, you see that the shallow neural networks are much better than linear methods on this convex hull. And this had already been known by Baron, but we essentially sharpened these rates, right, to increase the gap between the linear and neural network methods. And then the second result, this shows that if you require even nonlinear methods, if you require this approximation to be continuous in that sense, then even nonlinear methods cannot improve upon neural networks on this convex hull. So in a sense, the conclusion I want to draw here is this convex hull of sigma k of omega dot x plus b is kind of the right class of functions to consider for shallow neural networks, because shallow neural networks are optimal on that class, right? And we now know exactly what rates they can attain and exactly how big this class of functions is by having estimated the entropy. So yeah, that concludes the main part of the talk. And yeah, so I see I only have basically 1 minute left. So maybe the next thing I'd discuss here is the algorithmic aspects. So analysis of greedy algorithms for approximation. And here, let me just go briefly through this. So our next question was, can we actually achieve these n to the minus 1/2 minus 2k plus 1 over 2d, this sort of optimal rate? Can we achieve that using some algorithm? And we determined that the orthogonal greedy algorithm, right, which is given as follows. You start with your approximate being 0, and in each step you choose the dictionary element g that correlates most with your residual, right? And then you project the target function f orthogonally onto the span of the dictionary elements you've found so far. So of course, this argmax here, it may be very difficult to solve this for a given dictionary, and your ability to implement this method effectively depends upon your ability to solve this argmax, which is not necessarily a given. But if you do take it as granted that you can solve this subproblem, then the question is, so what rates does this obtain? Does this attain? It had been known that you can obtain this n to the minus 1/2 rate using the orthogonal greedy algorithm. But what we showed is that, in fact, you can obtain these better rates as well. So if this dictionary of functions has a small convex hull in the sense of the entropy decaying like n to the minus 1/2 minus delta, so decaying faster than n to the minus 1/2, then the orthogonal greedy algorithm attains that same approximation rate. And this shows that these rates that we derived can actually be realized using this orthogonal greedy algorithm, assuming that you can solve this argmax subproblem. And we have some recent sort of numerical results where we test this on PDE problems in dimensions 1 and 2, in which case this argmax can be solved relatively efficiently. So we're working on extending that to higher dimensional problems, more complicated problems. So let me now conclude here, right? So in summary, we've studied these approximation spaces for neural networks that consist of convex holes of these sigma of omega x plus b functions. We've determined the optimal rates you can get for shallow neural networks on these spaces, showed that shallow neural networks are optimal for this class of functions in a certain sense, right? And we've also shown that you can obtain these optimal rates algorithmically using the orthogonal greedy algorithm. So that's a summary here, and there's a lot of open problems here. Like, for example, how do you deal with deeper networks? We really have no idea how to deal with deep networks. This work is essentially only for shallow neural networks, where the methods are kind of different. You basically are looking at a convex hole of functions and doing nonlinear dictionary approximation. So we don't know how to deal with deep networks. In addition, we've done this theory for now in L2. So how can you extend it to p not equal to 2? We have some partial results, like we can get approximation rates and entropy, but the n-widths we don't know how to deal with for general p. And there's lots of other problems, like actually implementing this and demonstrating numerically that it works well. And there are also quite a few other open questions involving greedy algorithms. So I guess I'll stop here. Thank you for your attention. And are there any questions?
Thank you so much for this very interesting talk. Any questions?